and welcome to this lecture course on noise control in mechanical systems with myself Professor Sneha Singh from IIT Roorkee. So, we have been discussing about some case studies of noise in mechanical systems, and we have just finished the case study of a passenger car, and what are the typical noise sources within this passenger car, what are the mechanisms involved, what are the noise control methods used in the modern passenger car for a proper noise control. So, in today's lecture we will study about, so that is a second case study, which is the case study of a passenger train. So, again these are the common noise sources that we are discussing. We have discussed about a car, then we are discussing about a railway, which is a passenger train, then after that we will discuss about HVAC system as a case study. So, the case study of a passenger train. So, as you can see, this is one of the latest semi high speed train in India, which is the Vande Bharat, whose picture has been shown to you. And with reference of this particular train, we are seeing what are the various noise sources. So, as you can see, first and most importantly, the power source of this train drives it, which could be the engine or the generator which is utilized inside this train. Then you have braking system that is used, the wheel rail interaction, that is one of the major noise sources, and then the aerodynamics noise due to the airflow over the train, and the noise due to the horn and the whistles of the train. So, what you see is that the major noise sources, because both a passenger car and a passenger train, they are automobiles. So, they will have quite similar kind of noise sources and also quite similar kind of mitigation mechanisms. So, let us individually see all of these noise sources. Some other noise sources being the track irregularity, the rail joint interaction, the HVAC system that might be employed within this passenger train, as well as the chassis vibrations. So, let us see one by one. So, the engine or the generator noise, this is the power source of the passenger train which drives the train. So, it can either have an internal combustion engine or a diesel engine that is being installed, or electrical traction motors being used along with the cooling fans. Okay. So, in most of the new, slowly India is heading towards electrification of their railway fleet. So, most of the newly developed trains, they are coming as electrically powered trains, and there the electric traction motors are being used. But in some of the older version of the trains, and especially the trains operating in the area where the electricity line is still not continuous, there are, in some of these rudimentary areas, we still have the diesel engine trains. Then wheel rail interaction is mainly the noise due to the contact between the wheels with the rails, as well as whenever they are making contact, the various kind of noises could be generated. The first could be the rolling, just by the means of the wheels rolling over the rail, you get the rolling noise. Then there could be, because the railways, they are being spread all across India, and you have between any two rail tracks you have the joints, they are welded together. So, at these rail joints there could be certain disjoint, or at the time when the railways, they are turning and shifting from one track to another, at that time also there could be a disjoint or a discontinuity between the railway track, and all of these joints and discontinuities will lead to it will give you a certain jerk and vibration, and it will create a noise. As well as sometimes you have this high pitch noise that comes from the wheel rail interaction. The braking system, usually shoe brake friction noise is generated using the braking system of the typical passenger trains. Then you have the aerodynamic noise. So, the airflow around the locomotive body at the high speed around various other outer body components, such as the pantographs or various other exposed components of the train. Whenever the train is moving at high speed, the air flows around it, and due to this, turbulence is created and the aerodynamic noise comes. Then we have the chassis vibrations, that is usually the vibration from the frames, from the various other components as well as the radiation from the panels, all of this structure borne noise. Then let us see what is the typical engine noise that is created. So, as already discussed, the propulsion system used in the passenger trains are the diesel engines and the electric traction motors. So, the diesel engines are used in the regions where the electricity is not very reachable, and then engines generate combustion noise and mechanical vibrations. The electric traction motors, they are usually used in most of the modern passenger trains, and here the propulsion motors, they are much quieter. Nevertheless, they produce noise from the cooling fans and the vibrations. So, in the engine noise, what is the mechanism of the propagation of the noise? Okay, rather the mechanism through which the noise propagates. We already know the sources. The sources could be the engine itself, the cooling fans, or the vibration of the various components present in the engine or the motor. Then how they propagate through? They can obviously exist either as structure-borne noise or as airborne noise. So what happens in the structure-borne noise? The vibration from the engine, it propagates through the train structure, and these vibrations, they are transmitted through the mounting, the chassis and the other supporting structures, and they typically produce low frequency noise, as already discussed in the previous lecture, where we are making a distinction between the structure-borne and the airborne. We know that structure-borne, they are typically low frequency noise because those noise, they very easily propagate through the structures. Okay, so the high frequency noise, they attenuate. So low frequency noise propagates through the structure in terms of the vibration of various engine components, okay, and goes through the mountains, the mountings, the support structures and the chassis and other things, and finally enters inside the cabin. And not just that, engine noise can not only propagate as the structure-borne noise, it can also propagate as the airborne noise, and that could be due to the combustion process of the diesel engine, the process of combustion and the process of the release of exhaust will create the noise. And in case of when it is an electrically powered train, then the moving parts in the electrically powered train, the moving parts of the electric motor that are directly exposed to the outside atmosphere will again radiate the noise indirectly into the air as the airborne noise, and this airborne noise becomes typically noticeable during the high speed or when the air is accelerating at a high rate. Let us see the noise characteristics of the engine noise. So what you see here is, these are the various sources. We have the combustion noise, the piston slap, valve noise, cooling fan, the intake, exhaust, injection, gear and accessory. These are the various sources and the typical frequency ranges that are observed. For the combustion noise, you have between 500 to 8000 Hz. Similarly, for the exhaust, you have between again 50 to 5000 Hz and so on. And what are the factors that affect it? For example, in the case of combustion noise, it is the typical make of the engine and the pressure and the temperature at which the cylinder of the engine is operating will decide how much combustion is taking place and what is the noise produced. In the case of the piston slap as well, the skirt liner gap between in this component is going to decide the noise. The valves that are present, again the acceleration of the vehicle, because if it is accelerating at a high rate, a wide throttle condition is there, the valve will be opening more, there will be a more valve seat gap, and hence higher amount of valve noise will be generated, and vice versa. The cooling fans that are used in these engines and motors, they again create noise, and typically the noise depends on the engine speed, because the higher the speed of the engine, the more is the heat generated, the more is the combustion taking place. So more is the heat being generated, and hence you need the fan to move at a higher rate, which leads to higher noise in the cooling fan. In the same way, the intake, exhaust, all of them are directly linked to the engine speed, because the engine speed, or simply whatever typically you call it the engine RPM, this How fast the engine is operating will decide what are the number of intake cycles in 1 second, what are the number of injection or exhaust cycles in 1 second, and higher the speed, the more will be the rate of intake, the more will be the rate of emission of the exhaust, the more will be the combustion taking place, and hence the more will be these noise that are generated. If the gear system are being used in the engine, then the number of tooth in the gear will decide the frequency content of the noise. And for various other accessories that are being used, typical condition of the accessory, for example, the alignment of the accessory or the mass balancing, how much the mass is being balanced, whether it is aligned properly or not, the lubrication and the maintenance condition of these accessories will decide the level as well as the frequency content of the noise due to the other auxiliary components of the engine. So, from this paper what the authors have observed is that they measured the noise due to the individual components within the engine, and what is seen is that the combustion noise is the noise number 4, and the exhaust noise or the source number 1, they are the two most dominant noise sources. Now, what is the impact of this engine noise? High level airborne engine noise can propagate into the train cabin, and if the train cabin is not properly insulated, obviously it is going to cause disturbance to the passengers, and when the air is passing through, this airborne noise can propagate into the nearby environment whichever is present along the train route. So, what would be the mitigation strategies? Because we know that engine noise, it propagates both as structure-borne as well as airborne. So, for the structure-borne component of the engine noise, the typical vibration isolation strategies can be used. So, the mounting for the structure-borne noise can be used, and sound insulation can be done, or the engine can be enclosed. Then advanced barriers such as the residential area along the train route. If there are residential areas present along the train route, suppose this is your train that is moving and there are some residential areas, then typical barriers can be installed on both the sides to isolate the train noise from propagating into the residential areas nearby. The other source of noise is the wheel rail interaction noise, as seen in this picture. So, the wheel rail interaction noise can be either in the form of contact noise. So, what happens here is that this contact noise is generated by the rolling contact between the wheel and the rail. Okay. So, the contact noise is generated by the rolling contact between the wheel and the rail, and this is in the form of the impact noise that occurs when the wheel pass over the rail joint or any other form of discontinuities that might be present in the track. For example, whenever two tracks are being joined together using welding or something, or whenever there is a train in the change in the track, so any kind of such discontinuities that might take place will impact the contact noise. The curved track noise, typically when the train is going to move along and it is sort of turning along some curved path. Okay, this curved track noise. What happens is that continuously the path is changing, so continuously there is this disjoint or discontinuities in the smooth train track, and in this particular scenario some high pitch squeal noise is generated at the time of navigation, turning, and this is mainly because of the friction between the wheel slides and the rail. They create this tonal high pitch noise because of the friction during the turning paths. The rolling noise, so in the wheel rail interaction, just the mere contact, it propagates the sound. The passing through the curve generates high pitched squeal noise, and just the mere phenomenon of the wheel rolling over the track, This rolling phenomenon itself creates the noise, and this is the continuously generated noise which is present, and it is very dominant at high speed. In fact, what we have observed in the case of a car is that the rolling noise typically increases sharply with the increase in the speed, and very soon it takes over and becomes the most dominant noise. So, at low speed conditions, usually the engine noise is more dominant, but as the speed increases, the rolling noise takes over and becomes the most dominant noise source. And in the case of train also, the same pattern is observed, which means that as the speed of the train increases, the rolling noise becomes highly dominant. Now, let us see how this noise propagates. So, the wheel rail interaction noise is primarily structure borne noise, okay? Unlike the engine noise, where we have almost equal contribution of the airborne and the structure borne component, in the wheel rail interaction noise, the structure borne, there is a much higher contribution of the structure borne component of the noise, and the airborne component is low. So, the structure borne component is primarily because it is a structure borne noise, it is due to the contact between the wheel and rail, and whatever road inputs are there, whatever is the discontinuity or the roughness in the wheel rail interaction, it will be passed on as vibration and from the wheels into the rest of the structure of the train. So, basically this contact and curved track noise is the structure borne noise. It will propagate, and even the phenomenon of rolling will be perceived, will be passed on as the vibration of the wheel, and then which will further propagate into the body of the train as a structure borne noise. The airborne noise, again the vibration at the surface radiates in the environment in the form of noise, affecting the passengers and the nearby residential area. So, the wheel rail noise, as already told, dominates at the high speed conditions. Typically the squeal and the impact noise, they are in the high frequency ranges 500 Hz onwards, but the rolling noise, which is a continuously generated noise due to the wheel rail interaction, is more of a broadband frequency spectrum. It has small peaks around the specific frequency matching with the train speed and the track condition. Now, what is the impact of this wheel rail interaction noise? As already told, that in most of the trains, as soon as the train attains a certain higher speed, and most of the times the trains are running at high speeds, okay. So, for most of the duration of the run of the train, you can say, so for most of the duration of the run of the train, it is the wheel rail noise which is the most dominant noise that is being created by the train, and definitely it is the most dominant or the loudest noise. It is going to create a lot of disturbance in the urban community that is being located near the train tracks, in particular due to the squeal noise on the curved track. And usually, the trains, they are in the open area, they are in the open environment, and even then they are able to create a lot of disturbance when located near the residential areas or near human settlements. And this problem amplifies even more when you have such trains in the underground, in the form of some metros, the underground subways or the underground railways, or when the train is passing through a long tunnel, etc. So, in such enclosed areas, the noise amplifies. Why? Because now we do not have free field condition, now we have got a perfect reverberant condition, and then because of the reflections inside the underground or the tunnel, the noise further amplifies. What are the mitigation strategies for this wheel rail interaction noise? So, first of all, because most of the wheel rail interaction noise depends on what is the condition of the wheel and what is the condition of the track. These are the two most important things to take in mind. So, proper track maintenance is required. You can use techniques such as rail grinding, which will smoothen any kind of irregularities on the rail surface. It will lead to a reduction in the high frequency squeal as well as the impact noise. Then the wheel design improvement. So, the wheel tread profile could be optimized and maintained so that they create minimum friction and they create less noise due to the interaction with the track. Then some kind of vibration isolators or some vibration resilient materials such as the viscoelastic material such as rubber, etc. So these viscoelastic material, they can be installed at regular intervals in the track and the base layer. So what will that do is that it will break the vibration path and suppress the noise due to the vibration of the railway track that may propagate into the train. Then we have the aerodynamic noise. What are the causes of aerodynamic noise in the trains? Obviously, when the train is moving at a high speed, it is displacing the air around it or around its body. And just like in the case of a passenger train, so when the air is being displaced around its body, then turbulence can be created and fluid flow noise is generated. So the primary source is obviously the airflow turbulence which occurs around the train's outer body. So not just the train's outer body, even the pantograph, which is this particular component that is there at the top of each coach and the engine. So this component that is there in each coach at the top to derive the electricity from the electrical lines, even this pantograph, it is exposed to the air, and this apparatus, when it interacts, the air flows through a very haphazard way through this pantograph, and due to this a lot of turbulence is created, and this itself also creates a lot of aerodynamic noise. So here, just like in the case of car, now what we have is that in the case of the car, the turbulence was only through the interaction of air with the car's body, car's outer body. But here we also have the interaction of the, so we not just have the interaction of the airflow on the outer body of the train, but also due to the interaction of the airflow over the pantograph component. So what are the typical characteristics of this aerodynamic noise? It is firstly, most of it is the airborne noise. As the name itself suggests, aerodynamic, the noise is created by the air, by the turbulence in the airflow over the structural components, and it directly radiates into the atmosphere. So it is fully airborne noise. It originates from the interaction of the airflow and the train's outer surface, and it radiates directly into the surrounding environment. What are the typical frequency ranges? The aerodynamics noise generally falls in the high frequency range depending on the speed of the train. What are the strategies that we can adopt to mitigate this aerodynamic noise? So we need to reduce the turbulence that might be caused in the air when the air flows over the body, and hence more streamlined design is required. So it is again just the same case as that of a passenger car. You have streamlined design for the modern cars. In the same way, in the modern trains you can see this kind of streamlined design. So the outer body is having a streamlined design instead of having sharp bends. Okay, so instead of having sharp bends, now it is more streamlined and smooth on the outer body that can reduce the turbulence created. In the same way, because now we not just have the body, we also have the pantograph. The pantograph can create aerodynamic noise, so we can have some streamlined cover over this pantograph fairings, and this can also bring down the noise level. So with this, I would like to close this lecture. Thank you for listening.